So take an ellipse and consider the family of inscribed parallelograms, four-sided parallelograms, the family. This is a one-dimensional family on the ellipse. Here it is. Let me animate it. This is a one-dimensional family. It turns out this family is closely related to elliptic billiards. You can actually think of it as having a confocal caustic. And believe it or not, this family has constant perimeter. So all families of n-periodics have constant perimeters. So the family of inscribed parallelograms in an ellipse also has constant perimeter, but it does not have constant area. Okay, now let's consider a point on the ellipse, P. I can place this point anywhere on the ellipse, and I'm going to drop 4 perpendiculars to the sides of the parallelogram, the inscribed parallelogram. Now, because alternate sides are parallel, alternate feet of perpendicular with P are going to be collinear, right? So you get this collinear triple, and you have this other collinear triple. Of course, if I vary P, I get a different type of scenario here. It looks like these lines are always parallel over P, right? If I vary my 4 periodic, I get a set of rotating triples, but the collinearity is preserved. Now, interestingly, just to repeat the phenomenon, you can see here that over all P, my triples are going to be always the collinear triples. They are families of parallel lines. Very well. Now, this video is about a very interesting phenomenon. If I draw a polygon that connects these perpendiculars, if I animate the one-dimensional family of parallelograms like so, okay, the perimeter of the pedal polygon is varying, and the area of the said pedal polygon will always be varying. Okay, however, the product of varying parallelogram area with varying pedal polygon area, this product is curiously invariant. So this is the first phenomenon. Now, if I now, instead of animating over family of parallelograms, I animate over position of P on the boundary of the ellipse, like so, another phenomenon happens. The area of the pedal polygon itself is invariant. Of course, the area of the fixed parallelogram is invariant, so their product is going to be invariant. This is trivial, but what's not immediately obvious is the area of that pedal polygon is invariant, and I can choose another position for this parallelogram, okay, and I can change the eccentricity of my ellipse, and as I animate P, I get the same phenomenon. The area of the pedal polygon over all P is invariant. Now, let me go ahead and draw the average of these 4 vertices of P. Okay, so let's call this C0. This is the vertex centroid. And I'm going to also draw the center of this wedge-shaped region, so the area centroid of this pedal polygon. Now, curiously, these 3 points are collinear over all P. So you preserve the area of the wedge of the pedal polygon, neither of the center C0, the centroid of the average of vertices, so the vertex centroid, nor C2, the region area, are invariant. They're not stationary, but they maintain a curious collinearity with the generating point P. If I vary my polygon, I take it over here. Of course, the collinearity is maintained. Okay. I go to a different value of invariant area over P. I can change A as well, make this guy less eccentric. And as I now vary my position of P, the invariance right now is maintained over the area. Collinearity is maintained. If I vary my parallelogram, collinearity is maintained, Of course, area of the pedal polygon is not maintained, but the product of parallelogram area with pedal polygon area is preserved over here. Thank you very much.